settle down. If you arrive late and don't have a booklet, just wait. Wait till the end of the lecture. We're not going to use a booklet until the end of the lecture. Okay? I've also handed out weeks 8 and 9. So from now until end of next week. All right? So they're in front once the end of the lecture happens. Okay, so we start something new, as you figured out. Linear equations. Now, linear, you understand what linear means, right? Something to the power 1, right? So now we've got a couple of variables, multivariables. So you've got x, y, z, w, whatever. And you've got something, an equation that involves different variables and how many of the different variables, and we try to solve those. Now you sometimes have a system of linear equations. For example, if you're looking at a water system, and you've got 3 or 4 inlets and 4 or 5 outlets, right? And what comes in must go out, right? And the flow rates are different, all that. You then say, what is the equation that I can model to get that? You sometimes will get one equation. Sometimes you'll get 4 equations to model it. I was helping my husband the other day. He's a chemical engineer. And he asked for my maths 1 help. Oh, I was so chuffed. It was again flow rates. I was so chuffed, adding value there. Happy, chuffed. It's an old slang word. Old slang word. Sorry. I was so happy. Yeah. It's an old slang word. Sorry. 20 years ago slang word. Okay, shh. Okay. So, shh. Now, when you have, shh, we will look also at equations, like for example a plane, right? It has 3 variables, x, y, and z, right? And coefficients of that, ax plus by plus cz is equal to d, right? So we look at equations, 3 equations, for example, where 3 planes intersect. They could intersect in a line, that's 1, 2, and 3. They could intersect in a line. They could intersect at a point. So we've got 2 intersecting there. Sorry, 2 intersecting in a line, and then one of them there, right? And that will be 1 point common to 3 of those equations, 3 planes, right? Or they could not intersect at all, right? There's no common point where all 3 points intersect, okay? So we'll talk about graphically what that means, or geometrically what that means. But basically, linear equations, it's got, I don't know, you go to a grocery store and your shopping bill, right? And you decide to buy 6 oranges, 5 apples, and, I don't know, 7 bananas, right? Now, each item has a cost, right? So 6 times this plus, so just say I didn't know the cost, right? And once I go and I buy 6 apples, 5 bananas, 7, what did I say? Apples, bananas, and oranges. 6 apples, 5 oranges, and 7 bananas. And I get some value, right? The next time I go, I buy a different amount of each thing. And the next time I go, so now I've got 3 equations. I can figure out, not that I could just go and ask the guy, but I could figure out what the cost of each thing is by solving those equations. Now, we can solve them simultaneously, which will take a whole long time, or we could use computer software, which would be instantaneous, yes? Or we could use, we're going to do something called Gauss reduction, Gaussian reduction, where you put the system into a matrix, an augmented matrix, and we solve it. So today we're going to do lots of things, all right? But mostly theory, so hang in there. Hang in there. Hey? Time is a vector. Oh, limited vector. Okay. Shh. All right. So linear equations. No, let's start with linear equations. Shh. So the whole section, we call it linear algebra. And today we're going to look at linear equations, and we're going to start I'm going to introduce you to Gauss reduction. All right. So basically what we said, linear means to the power variables to the power 1. Remember that? And so we get ax plus by equal to something, right? Or ax, this is in R2, if we have to look at it geometrically. Ax plus by plus cz equal to something in R3, where a, b, c, and d are constants, and x, y, and z are variables. Or we call them variables or unknowns, which we often want to solve. So I gave you that example. I don't know, you could do flow rates with many coming in. I'll give you an example tomorrow with that. But you could do cost of vegetables, 6 apples plus 7 oranges, and 8 bananas, something like that, right? Just the idea of what we're doing. So I know in school you've been doing simultaneous equations, yes? So then, what happens when you get lots of equations, lots and lots of equations? For example, we've got this set of equations, a1x1 plus a12x2 plus a13x3 plus and then you'd get a1 in xn equal to b1. That's a b1. So that's lots and lots of variables, right? And lots of constants. The A's are all A11, A12, A13 are just names of constants. All right? They're just names of them. Okay? We can do another row, another row, another row. And we can fill this whole board with equations. So you get the idea. A23x3 what is this? A43x3. So you get the idea. Shh. Whew. I'll get tired, yeah. AM 1x1 plus a m. This was 1, 2, 3. This is supposed to be 2's. So you have many equations. The m is the number of rows of equations that you have, and the n is the number of variables that you have. All right? We call this m equations, and that's just giving you some ideas of rows. Okay? And how many you've got? How many unknowns? N unknowns. Right? Now, to solve a system of those equations, we have computer software to do that. But basically, you can do this by hand too. It'll take a long time. But there is a method, and we will talk about Gauss reduction in a while. Sorry, have I made a mistake? A31x1 plus A32. And that should be 4. Okay. 3, 3. Thank you. Thank you, Mandela. All right. Okay, so we're not going to do this simultaneously. So what we would do, not do simultaneously. Okay, that will take us very long. What we can do is put that matrix in something called an augmented matrix, and we're going to show you how to do Gauss reduction. All right? Okay, so the augmented matrix, and I don't want to solve a system like that. That's too big, right? So the highest we'll get to is to a 4 by 4 matrix that we'll do by hand. All right? Okay? So that means four equations, 4 unknowns. Okay? All right? So that's the highest we'll do. But to show you something simpler, okay? So we'll not do simultaneously. We will use Gauss. This is how you spell Gauss, G-A-U-S-S. Reduction, which is a technique which involves manipulating a matrix. Now, a matrix is just a rectangular array of numbers, okay? A matrix, do you know what array means? What does it mean? You guys are always complaining the English. Tell me what array means. Huh? Not you, okay. What does array mean? No? Array is just a sorted system. Array just means a sorted system, okay? A matrix, you must stop me when you don't understand something, is just a rectangular and I'll show you what I mean. Shh. So for example, we're going to look at this 3 by 3 matrix. You've got x minus y plus z equal to 2, x plus 2y minus z equal to 2, and am I doing this right? 3x plus 3y minus z equal to 6. So what we do is we take the coefficients of these values and we put it into an augmented matrix. All right? So let's go back to that board on the side. So we're going to put that into an augmented matrix. So basically it means I've got, if we think of it as planes, right? I've got 3 planes. Do they intersect in a point, in a line, or not at all? That means, do I have one value for x, y, and z? That's a point, right? Do I have many values for x, y, and z? Right? So I have many answers. Or do I have no answer at all? Is there no value for x, y, and z so that that system becomes consistent? All right? So we're going to talk about that now. All right? So in the augmented matrix, so you said into an augmented matrix looks like, so it is 1, 1, 3. That's for the x's, right? The y's is minus 1, 2, and 3. And the z's are 1, minus 1, and minus 1. Then there's a line here that represents the equal sign. All right? And then the values on the right-hand side are the constants, 2, 2, and 6. This is that put into an augmented matrix. All right? So, hence x. You don't have to write this all the time. Yes, question? No, not yet. I want it to be one matrix, augmented. Augmented. It just means augmented. Shh. Sorry, guys. So the matrix, and when we talk about a matrix, it doesn't have this line. All right? When we talk about augmented matrix, it's had something done to it, and that means we put a line there. That's all it means. Okay? All right. Shh. So let's talk about the geometric interpretations. Before we do that, we're going to look at the answers. Then we're going to look at how we solve it, okay? I want to do it, okay? Geometric interpretations. We'll do it now. Come on, there's lots of time. Interpretations of systems of linear equations. All right? So I did say it. I said it what I mean. So we could get a solution. So we get, 3 possibilities. You can't have all 3 possibilities. You can't have all 3. You get one or the other one or the other one. You can't have all 3, okay? So 3 possibilities. So the first possibility is a unique solution. So one answer. So we get something like x, y, z is equal to some values. All right? Some values there. Okay? All right? Don't want to give it letters. Just some values. Okay? So, and we write it as a column vector. Write as column vector. This is important in matrices because when we do something with it, we want to have it as a column vector, okay? So write as a column vector. Then the other one, so this is looking at your plane when they intersect at one common point. So that one point is in each of those planes, if you want to think of it geometrically. So this system is consistent. It has a solution. It has a solution. There was a question, Ty. Not do simultaneously, we will use Gauss reduction. Which one? Which involves manipulating a matrix. A matrix is just a rectangular array of numbers. Sorted system, array, sorted system. Okay. Sorry, my handwriting's getting worse as the years go by. I thought it's supposed to get better, but it's getting worse. All right, question? Okay, that was just an illustration or the theory that we can solve many equations, many equations with very many unknowns. We can solve those. We can do it manually. It'll take a couple of days, but they will get an answer. You'll get x is equal to something. X1 is equal to something. X2 is equal to something. X3 is equal to, so you can solve those equations. Okay? Just like how you'd solve a x plus y equals to 6 plus 2x, so the two linear, right, in 2D. So in multi-dimensions, or we called, when we say multi-dimensions, it doesn't mean we're in a different universe. It just means we're looking at different things, multi-variables. All right? So we can solve something. In engineering, you would look at cost, you'd look at time as constraints, you'd look at profit margins, you'd look at parameters for the equation, the reaction, something happening in a chemical reaction, right? All these things now, if you want to solve it, you'd get a surface or something, and you'd get one point, optimum point for your solution, if you're looking for a solution. So in real life situations, you get many variables, yes? And we often have to solve them. In what I'm illustrating here is just 3 variables, because I don't want to go do a long, big one, all right? It'll take a long time to solve, okay? So what we're doing now is just looking at systems with 3 variables, x, y, and z. We could call it x11, x1, x2, x3, but are just x, y, and z, okay? So it's got 3 variables. If we have a system where we have 2 equations and 3 unknowns, right? 2 equations and 3 unknowns. Think about that. AX, so you've got 2 planes, right? And where do they intersect? If they are parallel, they don't intersect, right? Your A, B, and C are equal, right? Or they're multiples of each other. Or if they intersect in a line, the only possibility, all right? And so we'll talk about this geometrically. So it's linked a little bit to vectors or planes, yes, and the section, all right? Yes, yes. So when we're talking about x is equal to something, right? Y is equal to something, we write it here, and z is equal to something there. Ask me, ask me. If you're confused, ask me. Guys, still confused? No? They don't want to talk to me. Okay, they don't talk to me. Shh. Guys, yes? Okay, let's look at this thing. These are the equations we're using. Right? These are the equations we use. Okay? So we take the first row. Right? First equation represents the first row. Row is this way, column is that way, right? Down. Column is down. So if I'm looking at you guys, there's rows, and columns. You guys are sitting in columns. Okay? All right. So this represents x minus y plus z is equal to 2. Okay, Mika? Hey? No. It doesn't mean shh. It doesn't mean x is 1. We're saying what is a constant in front of that x. So we're going 1x minus 1y plus z will give us 2. So we still don't know what x, y, and z are. All right? So all we're doing is, I'm going to show you how to solve it just now. All we're doing is putting it into an augmented matrix. All right? Once we put it into an augmented matrix, these are the possibilities we can come up to, and then I'm going to show you how to solve it. All right? Okay, guys. Shh. So the other option, so we're going to get 3 options. Your answer is going to be one of them. All right? So it's either unique solution or infinitely many solutions. Shh. What does infinitely many solutions mean? Points on a line. Yes? This could be 3 planes or 2 planes intersecting in a line. Okay? So you will recognize this way. So if we write it in our column vectors like that, we'd write it as whatever those values are plus lambda times maybe some sort of direction vector. Okay? You can recognize this, right? From when we did lines. Or the third possibility, which is, so this is also a consistent system, a consistent system. It has a solution. Or has solutions. All right? And then the other possibility is no solution, where no point common to 3 equations or 3 planes. All right? So we've got a system and it's inconsistent, meaning somewhere you've made a mistake because you're not doing the right calculations or setting up the right augmented matrix. That's in real life. When we give you a system to solve, you have to say either that it has a unique solution, it has infinitely many solutions, or it has no solution. Okay? All right. So this no solution means the system of linear equations is inconsistent. Inconsistent. I spelled it right. Okay. inevitably, when we're solving an augmented matrix, it results, so solving results in saying 0x plus 0y plus 0z is equal to d, a value. Now that is impossible. Okay? So that will tell us we've come to a dead end, or we can't solve it. It's not solvable. Not that we can't solve it, it's not solvable. Yes? Hey? Yes, sorry, d must not equal to 0. That's for no solution. Here, when we're solving, we'd get a row of 0. 0x plus 0y plus 0z equal to 0. And that will be infinitely many solutions. Okay? I will show you when we're doing examples how they fit in together. Okay? But I wanted you to know where we're going to along the way, because the solving is really simple. Shh. Okay, let's solve that equation. D is a constant. It's a value not equal to 0. Shh. There's a question in front, guys. Just hang on. Now I'll show you where we get it from. Okay? Hang on to your thoughts. 1 second. 1 second. When we're solving, I'm going to explain to you what happens. All right? All right, shh. If you want to call it K, it's fine. If you want to call it K, it's fine. All right? If you're happy with K, it's fine. It's just a constant. All right? A non-zero constant. Shh. Okay, so let's solve that one. Guys, now you can do it. There's ways in which you write these Gauss reductions down. Shh, guys. So follow a consistent manner. Don't change your method. So I'm going to show you one, and then the next example I'm going to show you another way. All right? So in this one, I put a line down the middle. Well, not exactly the middle. And for the first one, I put in what's on the left-hand side. 3, minus 1, 2 and 3, and 1, minus 1 and minus 1. Is that correct? 2, 2 and 6. So we put in the first augmented matrix like that. Okay? You can put brackets around it. You don't necessarily have to. If you want to, yes. But this is the augmented matrix. Okay? That represents 1x minus 1y plus z equal to 2. 1x plus 2y minus 1z equal to 2. 3x plus 3y minus z equal to 6. All right? And now we're going to solve it. Now the way we do this is, it has the method of simultaneous, but it's embedded in here. So what we're going to do is we're going to make these values in this diagonal, we're going to try to make that non-zero. All right? Non-zero. We're going to so I'm going to give you a hint here. Make the left, make diagonal non-zero. That's our aim. Okay? Because then we can say x is equal to something, y is equal to something, and z is equal to something, and make everything else zeros. That's the aim. But to do that, we have to follow operations. Now, operations means I'm going to manipulate each row, either by multiplying it or adding it to another row. All right, that's the only thing, adding or subtracting, multiplying or dividing by a constant. You can't multiply or divide rows. You can multiply and divide by constants to each row. Okay, I'll give you a list of rules just now. Well, tomorrow maybe. But basically, we start with saying, I'm going to make this, this one a 0, right? To make that position a 0, I'm going to say 2 times row 1, okay, plus row 2, right? Because if I had 2 times that and I added it to that, I'd get 0, wouldn't I? So watch what I do. So in the first row, I'm saying 2 of those plus 1 of that will give me 3. Okay? So I'm adding 2 rows. I'm multiplying the first row by 2 so that I get a 0 there. Question? The idea, one more time, I want to get zeros everywhere else other than the diagonal so that I can say x is equal to some value. So that's solved, isn't it? So I start with making those zeros and making the diagonal non-zero. And to do that, we have to follow rules. And those rules are, you can add and subtract rows, and you can multiply rows or divide rows by constants, all right? Not by each other. So what we've done here, we've said 2 row 1 plus row 2 will give us a 0 here. It's like basically saying, I've got 2 equations. You don't have to write this down. X minus y plus z equal to 2. And I've got, what if I multiply this by 2? Have I changed anything? It's still the same equation, right? And then I'm going to add the third row, x plus 2y minus z equal to 2, right? Then if I add those 2 rows, I get 3x plus 0y. What's this? Plus z equal to 6. Can you see it? Here I've got rid of one variable already. I'm closer to solving my equation. Right? So that's all it means. Right? We're doing the simultaneous equations without putting the x, y, and z, and in a systematic way such that I solve it like systematically and quickly.